Jokes aside, let's start this week's paper. This is about time clocks and the ordering of events in a distributed system, or how other people know it as Lamport clocks or logical clocks. And yeah, this paper is, I think, written in 1970. Am I right? Something like that.
Yeah, it's on the first page. I think it's 1978 at the bottom of the first page.
Oh, bottom of the first page. You already have it. So it's written in 1978, and it talks about distributed system, which kind of blows my mind. And I like not only does it talk about it, I think it defines what a distributed system is. It lays out a algorithm for distributed systems, and what does it do? It defines times. It's like the father of all distributed systems papers, and this is why I kind of decided to start here today. And from this paper onward, and the next couple of streams, we'll make our way into other baby childs of this paper. So, in the interest of doing it paper style, for those of you who haven't read the How to Read a Paper, there's a How to Read a Paper, and then the paper suggests that you should read a paper by looking at the introduction, and then abstract, obviously, introduction, browse the sections, and then look at the conclusion. So we're going to do a quick overview in the style of paper of this paper, and then we're going to dive in deep into all of the cool things that this paper produces. Are you with me, Raluca?
I am.
Wow, you're so excited.
I am actually.
Okay.
I'm looking at the year, so 43 years old paper. I think that's really interesting, and I think it's a really good choice for the first paper.
Thank you.
If we're doing this.
Thank you very much. So, as far as my understanding of the paper so far, the introduction just starts out very nicely by talking about how we perceive time, and then we perceive time in terms of how events occur and in what order. So I think this is just a great way to start out the paper, and we're going to focus a bit more on this one. Then, because he talks about order, he goes on to define partial ordering and a partial ordering operation in the partial order section. Then the next section would be logical clocks. So after talking about partial ordering and how their events are ordered in a system or in a process, he goes on and introduces the idea of logical clocks. And what's the next section? Next section is ordering the events totally. So I think this section starts talking about a distributed algorithm, right? On how to order the events in the system. And he talks about it from the perspective of a state machine, which I think is, by the way, good context about it. On his website, Lamport was saying that a lot of people had read this paper, and then a lot of people approached him saying that this paper was either groundbreaking or totally obvious, just because it has this kind of just lays out things in an obvious way. But then no one really mentions the fact that he introduces the concept of state machines and distributed algorithms. So we're just going to mention it right off the bat, so he can be happy with this. Anyway, next up, the section Anomalous Behavior kind of talks about what happens when we look at events not just inside of the logical space, but also real-time events, and introduces and goes on to introduce the physical clocks and how to synchronize them in the physical clocks section. After just laying down some hard math. It's not that hard, but it's very interesting math. He kind of proposes the theorem, and then that's mostly it. That's the overview. Cool. Well, let's go back to the top. So, section by section, let's duke it out. What things did you find interesting, mind-blowing, like that you want to share?
On the first page, one of the very interesting things that I found is actually in the note. If you look at the very end, like the last line of the note, it says the article actually costed 75 cents.
Oh,
So back in the day, this article was selling for 75 cents. Now, if you want to buy an article on the ACM webpage, it would cost £30, $30 or more. And I found that very interesting. But now let's get to the real things.
we've been ripped off.
Apart from that, I also I found interesting the way it is written.
In what way?
It's different. It is different to read a paper from 40 years ago compared to something that just appeared at OSDI or something like that. The language is different, and you can see that the way it's put in, like the introduction, the way it's introduced, the way the background is explained is, we usually think about time in this way.
Yeah.
Whereas nowadays we see papers that have a lot of they discuss a lot about workloads, about very specific technologies, about real numbers, how many people use a specific, how many people use Hadoop, how many people use Scala,
Yeah.
what are the drawbacks of the current systems,
Yeah.
and what people trying to sell the piece of thing that people want to explain in their paper. Whereas here we talk about time and how events are ordered in time. And I think it's useful to read something like that. The introduction is very easy to read for somebody who has experience, as well as for somebody who doesn't have much experience in the area. So the person would immediately see the benefit of the concept right from the introduction.
Wow, you kind of blew my mind because I didn't see it like that. I just thought Lamport has an amazing style. Like it's so poetic. But you're right. Like if you read research papers right now, like our algorithm is much better, or our proposition is much better compared to Chubby. If you haven't read the Chubby paper, go here, and then you're like browsing through papers and like, what does this do? Okay, this, and then they propose like these minor latency improvements, and then the way to achieve consensus. And yeah.
Yeah, of course, not every paper is like that, but yeah, it's cool to notice how few references there are.
And
And
most of them they're to physics books. So
yes, and it's not something that you see in current papers. So you do need a lot more background nowadays to read.
yeah.
So we have more history nowadays than we had 40 years ago. You have to incorporate it in your paper somehow, I guess.
Yeah, that's true. That's true. Or just because this paper was like so off the wall, like propose something different. There wasn't many references to inspire yourself from. Because I think maybe not. Maybe it's too much.
Yeah, it could be. Yeah, sure.
Yeah. Anyway, let's go. Let's go into the paper and talk about the algorithm itself. And like, there are many references to like physics papers, but why is it? Why do you think that is?
I think partly because, well, I don't find any. Am I missing something? I don't find references in the introduction.
Nah.
I think they are somewhere in like later on.
Yeah. Well.
Yeah. And in introduction, I see. So the reference that he's making of, it's the it's the ARPANET, the distributed systems system they have. It's not an actual reference to a paper, and it's not an internet link either, of course.
Wait a second, I lost your face. Okay.
So I'm just saying that the author references the ARPANET, even though they don't have a reference at the end or a link. And of course they wouldn't, I mean, the joke would be that they don't have a link. Of course they didn't have internet, right?
Oh yeah, yeah. Oh, ha, 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 ha. I got it. I got it now. I got it now.
So yes, they don't have, they talk about the ARPANET, the example of distributed system that they have, a bunch of interconnected computers, the state of the art of distributed systems at that time. And that's
That's and I think one of the things that I like is like we use the term distributed system, but then he actually goes on and defines what a distributed system is, right? So I quite like that. Like he's very specific about words and what they mean. Like a distributed system, he goes on and defines it as as we talked before, two computers or processes far apart, but then the messaging transmission between those two processes has to be non-negligible, because otherwise it can just be a local computer. So yeah, I just like the fact that he just goes right on and defines it, and then also starts defining this happened before relationship, right? Because he starts talking about time, and then he starts defining this idea of how we understand time, and then the fact that we understand it as a series of events that happen. And then he said that, okay, and then we have this happen before relationship, like one event can happen before. And then he kind of starts this whole paper just by looking at like these two basic concepts, which I think is just mind-blowing.
Yes, and I think at that, so for that time, it's also interesting to see that the paper attempts to generalize the idea of a distributed system.
Yeah.
Of course, they have the ARPANET, which is a distributed system as much as you can. I mean, a very good example of one. But they also it also tries to see the fact that you can have a distributed system in the same computer, in the same machine. So you have a communication between different parts of your system, like the memory and the processor and the network card and so on. So it kind of goes, it generalizes this idea.
Outside and inside. Yeah, that's true. And I think like his algorithm and the way he views it applies for multiprocessors or multi-threaded systems. So yeah, that's a very good point. Yes. And then partial ordering. So yeah, what is this partial ordering?
It starts talking about it introduces clocks. And so it tells right at the end of the introduction that they're going to talk about introducing real physical clocks, describing a simple method for synchronizing these clocks.
Yes.
And derive an upper bound on how far of synchrony they can drift. I think this is one of the important things, the meaty things of this paper, that they are deriving an algorithm to synchronize clocks on two distributed systems.
Yeah.
So first of all, we have the partial, when we talk about, so we talk about partial ordering because when you have two systems running two programs, you don't really care which things happen at which time, but you do care when they synchronize and when the messages are used together. So when you synchronize these two systems and you try to use it. So let's say you have C, which is equal A and B, and A would be a function A and B would be a function B, or a process A, result of a process A, and B would be result of a process B. If you run them in parallel, you don't really care which order it is. You only care that at the end, you get these results to calculate C. So you won't calculate one after C.
Yeah.
Right?
Yeah, exactly.
So you care about saying that A will happen before C and B will happen before C, but not that nothing between A and B. And that is a partial ordering.
Oh,
Um,
straight up. Yeah, yeah. I like it. I like it. I saw an example of defining ordering and why it's important in a system, and then why you should have partial ordering. But it was much more simpler in a way than yours. He was saying that, like the person was saying that if you have, for example, in this diagram, a person that's saying that, saying like the moon is made of cheese. I really like this example, right? And then the person says at P1 the moon is made of cheese, and then at Q2 Q person gets the message and says, oh yes, no, the moon is not made of cheese, right? And then if you would go back and then send this message to some other process R, then the process R would see the messages like the moon is not made of cheese first, and then but the moon is made of cheese, and then they're like the process R wouldn't know how to order these events, and it wouldn't make sense of the sentence that was just like thrown at him by two different people. So I think one of the things that I want to discuss is that I think it's important before we kind of move into talking about like partial ordering and the ordering of events is that this ties into special relativity, and like this is one of the main things that Lamport himself said that people that were studying distributed algorithms at the time, they were missing. They weren't taking into account the fact that, time is different if you are in different, like time is different if you are in two different parts in space, right? And then time just also, the further the points are moved apart, the further time just goes out of sync, basically, right? So I think a lot of people before Lamport weren't taking into consideration this special relativity principle of like time is different for two different points which are apart by space, right? So yeah.
I think this I don't think at that time it was that useful, but I think it starts becoming useful with us having robots on Mars and trying to do things like that eventually. So I'm not aware of any example that we're using this, but I can see that potentially that could be that's a good area. That's a good area for exploration.
Yeah, so we're going to go back to this paper when we're going to have messages sent to Mars, and then we're going to use this paper to synchronize the clocks between them. Cool.
Yeah, it wouldn't be the first time I actually find very useful resources in older research.
Yeah, and this is hopefully we'll uncover some useful resources. So one thing that I really like, again, about the introduction of this paper is that he defines, again, this happened before relationship very clearly in 3 steps. So basically, as we can see here, if an event A happens before an event B, it's basically A line B, right? And then also another relationship of happening before is the message, the sending of a message is A, and then the receiving of a message is B. So obviously the sending happens before the receiving, and this is relationship 2. And then I really like that he goes into doing a bit of, is this associative relationship? If A is B, B, C, and then AC, is this what it's called?
This is transitivity.
Yes.
This is the transitivity.
Yes, transitivity. I couldn't remember. Anyway, so I really like that he defines like these relationships very clearly, and then based on these relationships, he goes on later on to introduce the ideas of how time would basically flow in this like logical system of his, and then bind it with physical clocks.
One of the things that it is good to have a basis on, I think, are what total ordering and what partial ordering are. And I'm just going to give a small, very intuitive explanation of what these are. A total ordering, it is a relationship. Imagine numbers, natural numbers. in which every number is, so you have a relationship between every number. So you either have, let me take a step back. So if you have a relationship between A and B, so A is, let's say, smaller or equal than B,
Yeah.
and B is smaller or equal than A, it's only the case that A is equal to B. So that's one of the properties. The other one is transitivity, the one that you just mentioned. So if A is smaller than B and B is smaller than C, you immediately have A smaller than C.
Yep.
But we also have one that is very important for total ordering, which is the fact that you have a relationship between any two elements. So you either have A is smaller or equal than B, or B is smaller or equal than A, or actually both. If you don't consider equality, you just have A smaller than B, and or exclusive or B smaller than A. So you have a relationship between all the elements. In a partial ordering, you don't have the connectivity. So you don't necessarily have a relationship between all numbers. And that's exactly what happens in this definition. That's the definition of a partial relationship.
Okay.
You can, a partial ordering, you can take it as such. So you can have events that between which you don't have a relationship. So if you are to represent it, you would represent it as a directed acyclic graph. So you have relationships between some, but between some others, no.
So in this figure, because I got what you mean, but I wanted to give it like an actual example. I guess a partial ordering of events starting from P1 would be, as you said, acyclic graph P1, Q2, Q3, Q4, R3, right? And then a total ordering of events would be looking at all of the events. What would be a total ordering of the events?
For instance, you have a total ordering of events within each process. So P1, P2, P3, P4 are totally ordered because you can have only one process, one event for each process at a time.
Got it. Simple. That was it. Boom. Partial ordering and total ordering. Cool. Well, I think we smashed this section, right? Let's look at logical clocks and their introduction. So I think if we look at events, I think this is the best diagram. Like, we can just keep this diagram for the entirety of time, because we can just every section kind of refers to this diagram, right? So I think the concept of logical clocks, right? It would be just introducing any logical construct inside of processor, and then every time an event happens, you increase that basically that C value or whatever to some value, and then that's I think the most simple definition of logical clocks. How would you define the logical clocks, other than one value that gets increased whenever there is an event?
I think an intuitive way of thinking of it is that it introduces ticks or barriers. Stuff happens between these ticks. So the state of the system, let's say, changes between ticks, and you can only read the state of the system at the tick, when the tick happens. So for instance, you are in process P, there are some events happening, P1 is happening, and then you have the tick, the dashed line, and there is where you read the state of the system. That is where you can read the state of the system. And then you have something else happens, and then you read it again. Between these two, nothing has changed.
Yeah.
But then P2 happens, and next time you read the state of the system, and it is the state has changed again because P2 happened.
So question, when you define it like that, if you look at this diagram on the right, you have one tick that basically says, okay, these 3 events started in the 3 processes, right? And then you have another tick before the event is being received on Q2. Does that mean, I know that he defines, so in the paper he defines that every message when it's passed needs to go like through a tick line. So I was wondering, why does he do two ticks in the beginning in this diagram? Because you can see, I'll pull up this one because it's easier to look at, right?
Mm-hmm.
So he has one tick in here. It's basically processes, event started in the process, and there's another tick here. Like, I was wondering, do you know why?
I don't have an explanation for that, but I guess so I couldn't find anything. Maybe I missed it in the paper. But I think the idea is to see that multiple ticks can pass, so it's not necessarily, a tick is not related to an event. So the events may happen at different times. Just because events happen doesn't make the time go on. So the time doesn't go on just because events happen. The ticks just go on. The clocks move, but they aren't necessarily making the system. So they're not related directly to the events in the system.
Got it.
The time that they describe here is, first of all, is not necessarily the real time, at least not at this point in the paper.
Yeah.
It's not the real time. It's they even say there somewhere. Yeah, just at the end of logical clocks there. We make no assumption about the relation of the number CA of A to physical time. So we can think of the clocks CI as logical rather than physical.
Yeah.
They may be implemented by counters with no actual timing mechanism.
Yeah, exactly. Yeah, this is what I understood. It's like a counter, but I was wondering if it has some logic that I missed on increasing the counter twice in the first step, and then basically just it's almost like once every time an event happens. So there's twice in here, and then it's once, right? So I was wondering if there's something I missed or not.
No, and also one thing that I find misleading at this point is that these counters are independent for each process,
yeah,
which you can read from the first. So from figure 2, you can kind of read it because they are uneven. So the clocks are, at least at this point in the paper, independent of each other.
Yeah.
Each process defines their own clock, and it goes in their own way. Whether it happens, you have 1 or 0 events in that
time space. Yeah. Or
yeah.
I got it. Yeah. Well, it's not defined yet, but he's gonna go on to define on how this like time passes between processes, because is it next up? But anyway, the way I got it is basically he's gonna whenever he's sending a message, the timestamp will be sent in that message, and whenever another process is receiving, it will increase its timestamp to the timestamp that it received, or if it's way ahead of the other process, it will just keep it. It could keep it at whatever timestamp the process is right now.
Yeah.
Yeah.
One of the important things here, I think, is the clock condition. So the way they are, you're just on it.
Yes. Yeah.
The clocks are supposed to be at total ordering eventually, but at this point they have to preserve the ordering of the events.
The partial
so
ordering.
If A happens before B, then clock of A should be smaller than clock of B, especially for the same process.
Yes.
For the same process.
Yes, that is true. And again, this is what I like about this paper. Like, it's such a simple statement, right? Like, you can just look at it and you understand, like, oh, it makes sense. I understand it. And then he starts putting this clock condition into the two partial ordering conditions that he mentioned above, statements, sorry, that he mentioned above. For example, if A and B are in the same process, then obviously C of A is smaller than C of B. But then if the sending of a message is A, then Ci of A is smaller than Cj of B, because B would be the receiving of that message in a process, Cj. So again, it's just restating. It just feels like some mathematical proof. It slowly just moves in from a simple solution and then keeps on adding simple stuff. So I really like this. And I guess this is it with the logical clocks. Wow, we smashed that section.
I think there is one more thing that I found interesting, which is that even if you have this, it preserves the clock condition. So it preserves the happens before, the clocks preserve the happen before condition. The converse is not true. So they are not a direct thing. So they aren't just exactly the same ordering. So if the clocks, okay, let me get to that part. So we cannot expect that any two concurrent events to occur at the same time.
Oh yeah.
So if the clock would be the same in each of the processes, then that would mean that the actual events would actually happen at the same time, and we cannot expect that. It's not useful, and it's not realistic either.
Yeah, and I think again this kind of clicked in for me when I looked at figure 2, the one that's with like the skewed drawings. It's basically, if you look at it, P2, Q3, and P3, they're both concurrent because there's no partial ordering or no relationship in between them, right? So they're concurrent. So from the point of view of process Q, they wouldn't know if it wouldn't know if P2 happen or will happen, or the value, or P3, right? And then even though this diagram would show that P3 and P2 maybe, P3 will happen before Q3, when you go at this diagram, which is the normalizing, you can see that P3 actually happens before Q3, and then in diagram 2, P3 looks like it happened before Q3. And this is just because again, the events are concurrent, and then from the point of view of one process, maybe this event happened at a sooner time, but then when you actually look at it from like a systems view, you could see that actually it happened later on, right? So it is, yeah.
Right.
Yeah. Cool. Well then, what's next on this paper? I think we're looking at ordering the events totally. So, why is ordering of events totally important?
I think so. You have a series of processes with events happening, with a series of events totally ordered, but now you don't have it totally ordered.
Yeah.
But you can order it totally, because actually, I think this is related to the fact that if you have a two-dimensional space, and in each dimension things are totally ordered, then you can totally order everything else. You just number the dimensions. So here you have processes, and you number the processes, and you do an ordering on the processes. In this case, you will have P smaller than Q smaller than R. And if you don't know if two events are so in the process P and in the process Q and R, so in each process you will have event order totally, but between processes you don't know. So now because you know that process P is, let's say, smaller than process Q in their ordering, you put those events in process P that are ambiguous, you put them before process Q. So now you have a total ordering.
That is true. That is true. And then he goes on to do this exact thing in the context of solving, was it mutual exclusion problem? Solving the mutual exclusion problem. So if all of these processes, if they want to access a resource, they basically need to do a total ordering for their input queue, and then he goes in to define what an input queue is. So basically, if a process wants to access resources, it would do a total ordering of the events of the input queue, and then would access or not access that resource. And this is where, yeah. So this is what I kind of like. Like, he thinks of input queues and everything. So I think it would be helpful if we would give an example again by looking at this diagram of how this mutual exclusion problem would be solved with total ordering, right? So he gives, I'm gonna try and think. So for example, if we would have process P trying to access a resource, the algorithm that he defines goes as follows. So process P would give a message to process Q saying that, oh, I'm going to access this resource. And then it will send the message to process R saying that I'm going to access this resource. And it will also put a message on his own input queue saying, I'm going to access this resource. If the total ordering of the events in the process's input queue is showing that this process is the most recent one asking for the resource, then he accesses the resource, right?
Yeah. Yes.
One thing that I missed is, now that I'm thinking, is that every process has to reply back to this process P, or the process making the request. They have to answer back saying, okay, we acknowledge your request, because otherwise some other process could access it. So yeah.
It actually relies on two assumptions.
Shoot, where are these assumptions? Tell me the page.
Let me find them.
Well,
561? No.
Yeah.
4 out of 8.
561 where?
4 out of 8.
4 out of 8.
Yes. Here, to simplify the problem, on the right side column.
Yeah.
They make some assumptions.
Yeah.
So first assumption is that the messages are received in the same order they are sent. Which we know that it doesn't happen all the time.
Yeah.
We'll come back to this.
Yeah.
And the other one is that all messages are received.
Yeah. Which
so
we know
once they send
happen.
the message, they know the message has been received.
Yeah. So these assumptions.
I think that would mitigate your. So if these assumptions hold true, that would mitigate your concern.
Oh, with the request, yeah, with the request coming back,
right?
Yeah. But it's a lie.
Well, I think he's coming back to these assumptions in the next section.
Yeah.
Although I'm not 100% sure it's mitigated completely. We'll have to see.
Yeah, I think he at one point he says that failures can happen, but it's beyond the scope of this paper to handle them, which is completely true, because you need a lot of research papers to handle failures and messages between components in a distributed system. So yeah. Cool. Well, then this total ordering, as I said, In this section, he describes this distributed algorithm of how messages pass from one process to another, and then how they keep these messages inside of an input queue. And then when they need to access a resource, or whenever a message comes in or out, they do a total ordering of the messages inside of the input queue, and then they know should you access the resource or not.
Yes.
Which is straightforward, and is amazing. I don't know, every time I read about algorithms, I just want to go and implement them. Like, I would be curious of implementing this super simple algorithm and see how badly, and if it fails, and how, right? Like in an actual system. Maybe I should do a programming distributed systems algorithm. I'm much more comfortable. Okay, so this is all fine and dandy, this total ordering. Oh yeah, this is it. This is the part that he's very upset that people forget about. This is the part where he talks about the state machine. And then he defines these messages in between processes as commands, basically. And then he says that each process acts like a state machine. You have the current state, which would be the input queue. You get a command, and based on that command, you would get the next state of the state machine, because that's how state machines work. You have the current state, and then you apply something to it, you get the next state. So the commands that would modify the state machine, and the way that he defines them, are the request resource and the release resource, right?
Mm-hmm.
Which is pretty straightforward and is nice. And yeah, again, I thought it would be nice to mention this. Yeah, that's it. Yeah, that's mostly it. This is how this section ends, with the problem of failure is a difficult one and beyond the scope of this paper. So it's nice. And now we get to the real world stuff, how it actually applies in the real world. And I think he introduces the concept of problems that would arise in the real world very nicely. It's like, what if you send a message A from a computer A, and then and then you call your friend, which lives half across the country, and then he sends a message B from computer B. What's the total ordering, right?
Yes, or just simply sending a command on a Spark cluster. How do you make sure all machines have started at the same time?
Jokes. Stop. Yeah. So yeah, how do you make sure? And the paper very nicely goes and says that if you don't take into consideration the real world events, so up until now we were talking about logical events and partial ordering in a system, and that was all fine and dandy and we could do it. But if we don't really take into consideration these real world events, then how events look into a system might just become, it wouldn't make sense for an outside observer, right? Because we use time and we perceive time differently. Is that like a good assumption of what I read?
I think so.
Well then, let's move on forward. And then yeah, he goes and introduces these real world events, like calling your friend, or like basing your ordering on time as an external observer as a strong clock condition. Is that right? It's basically he starts looking at physical clocks right now, and then how to introduce these physical clocks into this total and partial ordering, right? Okay.
Yes, and this section strongly relies on a piece of technology, which are quartz clocks. And we know that quartz oscillates regularly, so it's very precise. So that's because at that time we knew that we could have this technology in computers. That you could have a real time clock, and not just something that increments, not just a counter that increments with time.
Wow. Can you imagine? Maybe at one point we'll have nuclear clocks, and then we won't have to bother ourselves too much with synchronizing clocks that often. Well, put your face on. Okay, so what I really like is that he talks about the concept of time in terms of how a clock would tick, right? So we can see here that the clock should
Yes.
tick at a rate of 1, and then he does this very simple differential equation, dci of t over dt. It's basically should be almost 1 because that's the rate of change of a clock, right?
I wouldn't want the audience to be scared at differential equations here. You can simply read those conditions. So condition 1 could be read just simply, it's a rule on the rate, which states that the rate is good. So it does have a constant rate, and it's small enough that you don't have to, it's high enough. The rate is high enough that you don't have to wait. You don't have multiple things executed at the same clock time.
Really? Is that how you interpreted it? That's pretty cool.
This is how I read it. So the rate is good enough that you don't have issues with the rate.
The rate's good enough that you don't have issues with the rate.
Sorry, the rate is that wasn't very intuitive.
Yeah.
It says that the clock CI must run at approximately the correct rate. So the rate is almost constant. So it's almost the same time between ticks all the time.
Yes.
Continuously.
Yes, this sounds better.
And the difference isn't that important, isn't that much that it actually affects the ticks significantly.
And for everyone that's wondering what the ticks are, it's for a quartz clock, 10 to the minus of 6. He even says it in the paper. So that's how accurate they are. Well, sorry, not how accurate. How far apart quartz clocks can grow. Like how quickly they can grow far apart. Yes, that's the one. Yep. And yeah, I mean, you will have to use your math background and talk me through what he's doing next if you remember. But I think he calculates an upper bound on how far apart clocks can go. And then whenever another process receives the message, you have this expected time that the clock can be like an offset, and then basically the new. So to take a step back and restate what I was saying, you have process P sending a message to process Q, and then process Q is basically looking at the time the message was sent from process P, but also taking into account this like calculated difference between the clocks that might happen. Is that right? And then it adjusts its own clock internally and always goes in front and never goes back.
I think so. I haven't gotten into the nitty-gritty of this demonstration, but roughly it proves that the anomalous behavior is impossible. So having problems with messages isn't going to happen. So it definitely relies on these conditions that it has on the strong clock, and to
what are these conditions? Are they the same conditions as the logical clock?
Yeah, no, these ones.
Oh, cool. I don't know which ones.
You're just on top of them, PC1 and PC2.
Okay, cool. Anyway, I guess,
And
yeah, go on.
so they just want to it wants to prove that the new system with these conditions still satisfies the strong clock condition, and that was stated a few pages above.
Well, I would be curious to know how he got to the idea of it's impossible, but the proof was a bit too much for me. So I'm gonna take his word for it. Yeah. Well, with that one, I guess this is it for the paper. The idea, the concept of happening before was defined. Uh, an algorithm for synchronization was also proposed. Which uses total ordering, and then he also defines this upper bound limit on how far apart clocks can grow in a system, right?
Yes.
Well, I guess this is deserves a clap, a silent clap. Were you still looking at the paper like your math skills were like, I have to solve these equations, and then 5 minutes later, Raluca, wake up! No, I haven't solved them yet.
No, I was actually looking if we covered the fact that to describe the simple method of synchronizing these clocks. So I'm not sure if we explicitly discussed that.
Let's explicitly discuss that. Go on. What you had in mind?
I have to find it.
I mean, you can give an overview and then I'll find it. I mean, I guess the synchronization of clocks just happened when the messages were parsed, right?
Yes, I think it's no, it has a specific thing here somewhere.
Is
Let me
there
find
something
it.
more specific? Oh, then I
Oh, it's in the it's it.
got
Hmm. Just give me 1 moment.
sure.
Yeah, so the algorithm is in at page
561.
61 or 4 out of 8.
Okay,
On the second column,
this one, right?
the algorithm, yes, this is one. So this is the algorithm he proposes for synchronizing clocks.
Yes, and then where's the clock synchronization happening? Like the thing that actually states that process PI is granted the resource when the following two conditions are satisfied. This one?
No, the algorithm is 1 to 5.
Yeah, 1 to 5. Do, 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 do.
Yes.
Okay,
Yes.
yeah.
Um,
But it's the same algorithm that we talked about when we talked about state machines, right?
yes, yes. I had the impression that we didn't explicitly say that, but
We
I
we
might have missed that.
we can go back and say the finite state machine example explicitly stated this algorithm for synchronizing clocks. And then now we're done? I guess so.
I guess so.
Okay, so any other ideas that you got from this paper before we part ways there? You're still trying to solve the math problem right now. Like,
No,
what?
no, no. I think just give me 1 moment. I think I might have, so I'm not sure. I I'm not sure that's the right algorithm.
Wait, we have a question in chat. Sorry for not paying too much attention. By the way, this is super new to me. So I'm going to read out the question in chat. What do you think of this algorithm's application to systems that depend on real world clocks? As every process assumes the correct time to be the max time, the system would drift further away from real world time as the system continues to run.
I don't think the paper considers all the problems of the real world systems, especially not all the problems in which large scale distributed systems contain. Nowadays, if you don't test it on at least a few hundred machines, it's not real. But this is a theoretical paper, first of all, so probably wouldn't get into that category. But I agree, it doesn't touch on many corner cases. It doesn't talk about faults in the system, and it doesn't talk about and the algorithm of synchronizing clocks should be run multiple times. As the commentator said, they would drift apart after a while.
So should it be run then something in the background, like a background thread? Yeah, but then that's a good question. Maybe I'm trying to think, because he says that you can never, like the paper says that you can never set a process's clock backwards in time, so you can only move it in forwards in time. So, like, I think this comment is very good, that each process would say, okay, I have my max time, this is the right max time, and I can never go back, I can only go forwards, right? So in a sense, the process that runs the fastest sets the time for the other ones so they can be in sync. Would that be a good way to reason?
Yes, actually it does say, I don't think I found the right algorithm. So I do remember when reading it, I do remember that the idea was that process sends the clock time at their so when sends a message with their time, and the receiving process will then set their time according to that one.
Yes.
According to the clock received, and ensuring, knowing the ordering, that would ensure, eventually a total order.
But then, sorry, go on.
I think that would help.
Okay, but then, yeah, because I was thinking if there's any corner case where the system would just. Okay, so no, this is another facet of his question of like, damn, this is a very good question. I didn't know people can post these questions like this. I love Twitch. So, for example, let's say we have the system has been going, for like a couple of hours or months or weeks, and then the time in the system, even though it has been synchronized initially by clocks and it has been synchronized in between processes, right? We're using this synchronization method. It has grown very much apart from what the real world clock would be, because you have process one, process P and process Q, and then process P would be like, okay, take my time because I'm further ahead in time, and then when I send you a message, basically you're taking my time, right? Like you're setting your clock to be equal to my time if it's further than yours. This is one of the things that this paper says, right? When it's talking about, and then at one point there's this risk of just these clocks going further and further and further ahead of the real world, right? Or is this being proven not to be the case?
Oh, I see. Yeah, I don't know. I'll have to think about this.
Yeah, we'll have to think. We'll get back to you on that. I'll po- I'll post it on Twitter. But it's a good question. Hmm. But how would we solve it? So if machines, maybe like a heartbeat message through the system that sets the clocks to a more normal baseline. I don't know.
I think it's not so much about setting the time in the paper as it is about setting the ordering, um, creating the relationship between events. So you won't change the clock. You will only change you will only reconsider the relationship between the events. Now, if you are to change the clock, you would rely on a authoritative source of information.
Yeah.
Relying on other computers on other machines that are possibly drifting further and further away from the truth is going to be mitigated by just having an authoritative source
Yeah.
of time.
Yeah. That's what I thought. But then it would be interesting to see how you would pass that authoritative source of time through the distributed system, right? Especially in real world scenarios. But that is
Oh yeah.
that's an interview question or something like that. And a question for another stream. Cool. Well, I guess we should close down. That was good. How do you feel? Closing
Oh, that was
remarks.
good. That
That's
was a
good.
good read.
Oh yeah, yeah. I think it was a good read as well. And as I said, I really like Lamport, like his style of writing minus Paxos. And yeah, hopefully we'll get more interesting papers in the weeks to come, the months, the years, because this has been fun and has been a good exercise in trying to explain and remember everything. So cool. Thank you very much, Relka.
Thank you, Bogdan.
See
Thank you all.
you.
Have a good day. Have a
Yes.
good evening. Bye.
Thank you all, chat. See ya. Have a nice day.